In this chapter, we're going to be talking about states of matter. The first state of matter we're going to talk about is gases. We're going to talk about the nature of gases and something called the kinetic molecular theory. So, kinetic refers to motion. The energy an object has because of its motion is called its kinetic energy. And the kinetic theory states that the tiny particles in all forms of matter are in constant motion. There's three assumptions to the kinetic theory of gases. The first one is that gases are composed of tiny particles, usually molecules or atoms. You can think of them as small, hard spheres. They have an insignificant volume and they're relatively far apart from each other. There's also no attraction or repulsion between these particles. The second assumption is that the particles in a gas move fast in constant random motion. They move in straight paths and they change direction only when colliding with another or other objects. This is the idea behind how you can smell a skunk from the other side of town. As soon as a skunk releases its spray, the particles that contain the odor are carried in the gas in the air, and they move in relatively straight paths and incredible speeds until they travel in all directions and eventually to your nose where you can pick up the smell of the skunk. The third assumption is that collisions are perfectly elastic. That means that the kinetic energy is transferred without loss from one particle to another, and the total kinetic energy of the particles remains constant. Another thing we can talk about when we talk about gases is gas pressure. Gas pressure is defined as the force exerted by a gas per unit surface area of an object. This pressure, this force, is due to the force of collisions of the gas particles on the object and also the number of collisions. These collisions are more forceful or more frequent, gas pressure goes up. The atmospheric pressure results from collisions of air molecules with objects. And this decreases as you climb a mountain because the air layer thins out as the elevation increases, so there's less collisions from the gas due to the force. Barometer is a measuring device that we use for measuring atmospheric pressure. And this is dependent upon things like weather and altitude. So the first device for measuring atmospheric pressure was developed by Evangelista Torricelli during the 17th century. And he called it a barometer. If you break that word down, baro means measure, and actually baro means weight, and meter means measure. So he's basically measuring the weight of the air above the measuring device. So the SI unit for pressure is the Pascal, and at sea level, atmospheric pressure is about 101.3 kilopascals. There's some other older units for pressure that include millimeters of mercury and atmospheres, both of which came from using a mercury barometer. You don't really use millimeters of mercury in Regents chemistry, but you will use atmospheres and kilopascals. So here's how the barometer works. It doesn't really work this way today, but this was how Evangelista Torricelli made his first barometer. So he had a dish and he filled his dish with mercury. He then put a glass tube in the dish that was under vacuum, and it was open to the bottom once it was under the mercury. The atmospheric pressure above pushed down on the mercury, and it had nowhere else to go but up into the tube. And if you measure from the bottom of the tube to the top, at standard atmosphere, at sea level, I should say, the mercury rose 760 millimeters. That's why we get that unit of millimeters of mercury. That's how high the mercury rose up the tube. So if this was at sea level, we call this standard atmosphere. And that number, 760 millimeters, is equal to a new unit, a derived unit we call 1 atmosphere. It's also equal to 101.3 kilopascals. So these three numbers are all equivalent to one another, and you can use them in conversion factors to convert from atmospheres to kilopascals or vice versa. For gases, it's important to relate measured values to standards because some of the variables can change at different temperatures and pressures. So standard values are a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals or 1 atmosphere. This is what we call standard temperature and pressure, or STP for short. You don't need to memorize these numbers. It's right on the front of your reference table. But you will probably see these two numbers, 101.3 and 1 atmosphere together a lot, and 0 degrees Celsius together a lot, that you probably will come to memorize standard temperature and pressure. So let's talk about what happens when a substance is heated. So as we add kinetic energy to the particles, let's talk about the particles in our thermometer here, these red colored particles. As we add heat to the particles, they gain kinetic energy and they start moving. Like the mercury, they have nowhere else to move but up. So the temperature rises in our thermometer, and that's why it goes higher up the tube, because the particles have more kinetic energy, or energy of motion. They're moving up. As it cools, if we take away this heat, they lose kinetic energy, and they don't have the energy to stay as high as they were in the tube, and the temperature falls back down. So eventually they will fall back down, but the particles are still moving. The kinetic theory says that particles are always moving. But is there a point where we could take away enough kinetic energy so they slow down enough to stop moving? So if we could look on a microscopic view of the particles in our thermometer here, they're always moving, even when they're solid. They're just shaking and vibrating in place. But there actually is a point where they can slow down enough to stop moving, or at least in theory there is. And we call that absolute zero. Absolute zero is 0 degrees Kelvin, or in Celsius, negative 273 degrees Celsius. So that unit Kelvin there, that's invented to basically define absolute zero. This is the temperature at which the particles would have no kinetic energy. If you cooled them down enough and took enough kinetic energy, there would theoretically be no motion. So this is how the Kelvin temperature works. It's a direct relationship between temperature and kinetic energy. So at 100 Kelvin, if I go up to this line and over, I would get a specific amount of kinetic energy. This is just a fake graph, so we'll call it X. But exactly double the temperature, I get double the kinetic energy. I would get 2x. But we could work backwards to where we got no kinetic energy, and that's what we would call 0 Kelvin. This temperature scale was invented to make the math that we're going to do in chapter 14 work a lot easier. In the Kelvin scale, there's no negative numbers. And if we dealt with Celsius, there would be, and the math would be a little trickier to deal with. So in summary here, you need to know the 3 assumptions of the kinetic molecular theory and how it explains gas behavior. You need to be able to define gas pressure and explain the variables that can affect it, and know what happens to the kinetic energy of particles when energy is added to them or taken away.